So our last speaker this afternoon, evening, is Fernando Cukierman from Universidad de Buenos Aires on deformations of exterior differential ideals and applications. Fernando.
Okay, thank you very much. Thanks for thanks to the organizers for such a nice workshop and for the invitation. Okay, so I will talk about the deformation theory of these objects, which are exterior differential ideals, and applications. The applications refer to applications to the geometry of the moduli spaces of these exterior differential ideals. Okay, so I will try to start with the basic definitions and motivations. The motivations, the differential ideals, they are related to the foliations. The foliations that are studied in differential geometry usually are non-singular foliations, and they correspond to the FAF systems or ideals of the exterior algebra. But here we have a slightly more delicate situation because we will consider foliations with singularities and differential ideals with singularities. So, but the motivation is the study of the problem of the irreducible components of the moduli spaces of foliations. I will say a few words, but this is an active area of research. So this is the motivation. It's not known what are all the irreducible components of the moduli spaces of foliations. So this is our motivating problem. Okay. So then we will consider deformations. Well, deformations of foliations have been considered before, and we will consider deformations of a more general object, which is an exterior differential ideal. So I will speak about the basic material on this also. And then to apply this in examples, we need to do some calculations of infinitesimal or first order deformations, or infinitesimal deformations, or tangent spaces to the moduli spaces. So I will. So this involves some delicate linear, multilinear algebra and exterior algebra. So I will talk about this afterwards, and then I will explain some of the applications we obtain, which basically are the stability of some types of ideals, of exterior ideals. Mainly, I will speak about FAF ideals and pullback ideals. These are the two types of ideals that I will mention in this talk. All this is a work in collaboration with Cesar Masri. Okay, so that's basically the plan of the talk. Our setup is we will work on a smooth projective algebraic variety over the complex numbers. Some of these things it is of interest to do them over other fields, but I will stick to the complex numbers. The variety X in principle is like this, but mainly I'm interested in the case in which X is the projective space. Well, L is a line bundle on X, and we will take a omega 1 form on X, a twisted 1 form, because it's a section of omega 1 twisted by this line bundle. And we consider the space of all these differential forms projectivized. This is a big projective space, which I call P capital N. And inside this space of 1 forms, we will consider Fxl, F is for Frobenius. These are the one forms that satisfy this condition. This condition is the Frobenius integrability condition. So if this condition is satisfied, omega defines a foliation, codimension 1 foliation, singular foliation. So basically, then this is the moduli space of foliations of codimension 1. Inside this big projective space, this condition, when we think about it, amounts to quadratic equations, because this is quadratic in omega. Omega appears 2 times. This is a quadratic condition in omega, and this is equal to 0. These are many quadratic equations. Okay. The number of quadratic equations is actually bigger than the ambient space, this number n. So this variety that we are trying to understand is excedentary. It's not a complete intersection. It's not clear what dimension it has, and it's not clear which are the irreducible components of this variety. So this is one of the main problems that we want to solve. But the problem is due to the fact that the number of quadratic equations that we're considering is very large. In a similar way, we can consider FQXL is a moduli space of foliations of codimension Q. But I will stick mainly in the examples, at least, to the case of codimension 1. So again, one is interested in the geometry of this space, in particular describing its irreducible components. So let's take a look to a few simple examples. So suppose X is Pn, then the line bundle is some O of D. Omega is just written like this, is a one form with coefficients which are polynomials, all of the same degree. The degree, I call it d minus 1. I call it d minus 1, the degree of these polynomials, to say that the form has degree d, because the d of xi have degree 1. So this is a homogeneous one form, is a twisted one form by the line bundle O of D, exactly because it has degree d. Okay. So we can think about it as one form in affine space. This form in affine space, to define a form in projective space, to descend to projective space, has to satisfy this condition. The contraction with the radial vector field is 0. So the coefficients AI should satisfy this condition. This is a reformulation of the well-known Euler sequence for the omega 1 in Pn. Okay. So we will consider, we simplify a little bit the notation, and in the case of Pn and the line bundle O of D, we simply denote it Fnd. So this is the set of one forms in Pn of degree d, which satisfy the descent condition and the Frobenius condition. For such a form omega, the singular set of omega is the set where all the coefficients vanish. Okay, so this is an algebraic subset of Pn, which has its own interesting geometry. Okay, if omega is an arbitrary form which doesn't satisfy the Frobenius condition, the singular set of omega, if omega is generic, is a finite number of points. But if omega satisfies the Frobenius condition, the singular set could be different. In general, it's different from a finite number of points. Let me show you one example of one forms that satisfy the Frobenius condition, okay? So these are called the logarithmic one forms. So we fix numbers n and d and before, and we fix another number n, and we will consider a partition of d in m parts, okay? So the di are positive integers. A differential one form in Pn of degree d is said to be of logarithmic of type d if it can be written like this. So this part here is a logarithmic form. Is dfi divided by fi multiplied by some complex number. This complex number is the residue of omega along the hypersurface fi. And then we multiply everything by f. F is the product of the fi's. So, because I want to talk about polynomial forms, not rational forms. This logarithmic part is a rational form. I want to make it polynomial. So we multiply by f. So when we do that, we can rewrite it. If we distribute this f, it cancels f with fi, and I have these factors, which I denote fi hat. So the logarithmic form can be written like this, okay? It's a very simple calculation to show that any such logarithmic form is integrable. And it is a theorem of Omegar-Calvo that the collection of these logarithmic forms with a fixed partition is an irreducible component of the space of foliations. Okay, so this is the first example of a family of integrable forms, and the theorem by Calvo says that this family is complete. It forms an irreducible component. So any deformation of a polynomial of a logarithmic form is another logarithmic form. It's a complete family. Or we also say that these logarithmic type forms are stable. So if you move them a little bit, you don't find anything new. Okay, keeping the integrability condition. Okay, so this is an important example of integral forms and of components. So for a fixed number degree d, you can look at all the partitions of this number d, and for each partition you have an irreducible component of the space of the space of foliations. There are other components. These logarithmic components are not all of them. We know that there are others in most cases. Let me show you other types of integrable forms, other known components. Let me just do it in codimension Q. So let me call, we'll talk about foliations of codimension Q. One way to obtain foliations is just to consider a rational map from Pn to Pq, for example, a linear projection from Pn to Pq for Q less than n, or any polynomial rational map from Pn to Pq. And we look at the fibers of such a rational map. The fibers of the inverse image of a point in PQ these varieties, they form a foliation of PN. These are the fibers of this rational map, okay? The fact that these are irreducible components, we proved in a paper with Jorge Pereira and Israel Weinzencher that this, that if you just vary the rational map and you deform such a thing in the space of foliations, you only find another rational map. Okay, so these are also stable. Another construction of another construction of irreducible components is what we call a pullback foliation. It's a generalization of this. Let's take a map from Pn to P2, and suppose we have some foliation in P2, and then we, let's call it eta, is a one form in P2 of degree D. We pull back eta by pi, and now we vary pi and eta, both of them, okay? It's easy to see that for any pi and for any eta, this pullback is this omega is integrable, okay? And as we vary pi and eta, we get a family of integrable forms, an irreducible family of integrable forms. And it is a theorem of Dominique Servault, Alcides Lins Neto, and Bas Eriksoven that this family, again, is complete for linear projections, okay? Is a complete family. One can do this also for maps from Pn to P2, which are non-linear, okay? Also, there is a similar result in such a case. So this is another example of a component which is different from this one. Another type of foliation is the following. Is a kind of foliation that Sebastián Velázquez was talking yesterday. You take an action of an algebraic group, a linear action, and then you take the action in Pn, and you look at the orbits of such an action. These constitute a foliation, a singular foliation, because the singularities will be where at the points where you have non-trivial stabilizers. Okay, so it's a foliation with singularities. So the orbits are the leaves of this foliation. And if the group satisfies some conditions, and the action satisfies some conditions, these foliations are stable, actually they are rigid, but they constitute components. This is something we proved in our work with Jorge Pereira. And for example, if you take the example where the group is semi-simple, and another condition, you have this stability result. So this is another example of an irreducible component, which is completely different from the previous ones. There are other examples of irreducible components. There is a famous paper by Servault and Lins Neto where they showed that in the case of foliations of degree 2, the number of components is 6. In this case of low degree, they are able to determine all the irreducible components, and there are 6 components, and they are described. There is a survey by Lins Neto. Well, the survey was updated is 2007. there was some recent progress, like for example, Pereira and collaborators, they made some progress also. So maybe a more updated reference would be this paper by Pereira, but up to 2007, this is a nice survey of the known results. Okay, so we will consider now, so this is the motivating situation with foliations. We will consider now a more general object, which is an exterior differential ideal, and study similar problems for these ideals. So again, we take a smooth, say, projective algebraic variety over C. Omega sub x is the algebra of exterior differential forms. It is a sheaf of differential graded algebras. An omega sharp module, by this I will mean a graded module over the exterior algebra, where each graded component is a covariant sheaf, and this is a finite sum. Only finitely many are non-zero. Okay, but it has a structure of algebra over the of module over the exterior algebra. Okay, that I will call omega sharp module. You will see why in a second. Okay, and morphisms of these guys are morphisms of degree 0 of graded modules. Of course, respecting the morphisms of graded modules over this ring. Okay. By an omega module, I will mean a differential graded module that is as before, but we have a differential d of degree 1. So d squared is equal to 0. This map D is not supposed to be of, it doesn't respect the structure of O module. Is only is a differential operator of degree less than or equal to 1. So it doesn't respect the O module structure, but is only of vector spaces. Okay, it's a differential operator of degree less than or equal to 1. And the morphisms between two such modules, they are required to commute with D. So this is an abelian category with enough injectives. It was considered for the first time by Herrera and Lieberman. Okay, some people call it the Herrera-Lieberman category. So this will be a category of modules which will work satisfactory for the things that we want to do. Okay. The reason is that we will consider omega. We will consider ideals. So sub-modules of omega, which are graded and are stable by the differential. Okay, this is what you have in the books in differential geometry, when they talk about exterior ideals, okay, or FAF ideals. This is basically the same. Okay, so according to our definitions, we have these inclusions of the homes. Okay, these are all linear. These are the ones that respect to the action of oh, sorry, no, I think this is not okay. No, forget this. This is not okay. I don't need this, but let me just skip that. We also can consider morphisms of higher degree R, so morphisms that increase the degree by R. So this is the same as a morphism from F to GR. Is the morphisms in the previous sense into the shifted complex. Okay, so in this way, the collection of all the graded morphisms from F to G of different degrees, okay, this is a complex, okay? So we can calculate, if we have a morphism, we calculate its D, which is defined like this, okay? So this in turn is a complex. And it turns out that if we look at the D, from this into this, as I just defined here, the kernel is just the morphisms that respect the D. So these are what we call Om sub omega Fg. Okay. So the Hom over omega and the Hom omega sharp are related by this exact sequence. So basically, these are the cycles in this complex, the kernel of the differential. Well, this is the general definition for modules. Okay, I'm going very, very slow. Sorry, I don't think I'm I'm going to finish what I want to say, but let me just continue. So we are basically interested in modules which are ideals, okay? Ideals of the exterior algebra, stable under the derivation. So, and we would like to study the infinitesimal deformations of such ideals, okay? Basically, this is the Hilbert scheme over the ring omega, okay? Because Hilbert scheme means ideals in a ring, and so this is this. We call Hilb omega the set of all the differential ideals, okay? We have this condition, which is the integrability condition, the stability under D. So that makes a difference, but actually, there is a very important paper by Artin and Zhang where they developed a general theory of a Hilbert scheme over non-commutative rings. Okay, so using the result of this general paper, we know that this Hilbert scheme exists. Okay. It's important in what follows the complex, when you have an ideal, this quotient is a module, okay? It's the ring modulo the ideal, and it has a differential. This may be thought of as the rank complex of this object. We can, if we like, you can think about it as a subscheme of I is non-commutative situation, but you can think about this as the rank complex of this non-commutative scheme, if you like to think about it. This complex appeared before is what appears under the name of leaf complex, introduced by Gomez-Mont. And also Bryant and Griffiths consider a complex, not exactly this one, a modification of this one, in a paper they have, which is where they study what they call characteristic cohomology. So when an example of a differential ideal is what we call a Pfaff ideal. A Pfaff ideal is an ideal which is generated in degree 1. So it's a differential graded ideal which is generated by the component in degree 1. This means basically that you have you start with subshift of omega 1, and you multiply its elements by any forms of the appropriate degree, and you take the exterior derivative in the sense of the derivative which you have in the forms, right? So this lives in omega 2, and then you multiply by any exterior form of the appropriate degree. So this would be the ideal, the differential graded ideal generated by this component of degree 1. So this is what we call, well, we call this an ideal generated in degree 1. A Pfaff ideal will be an example of this sort, but which satisfies this condition that d of omega 1 is contained here. So basically, when you have this, you don't need this part. The ideal is already generated by the algebraic part. So the ideal under these conditions is generated algebraically by omega 1. You don't need the exterior derivative because the exterior derivative is already taken care by this. Okay, and we call we say that a differential ideal is a singular Pfaff ideal if it is generated in degree 1 and in some Zariski dense open set satisfies this condition as before. So it's a Pfaff ideal in an open set. Okay. So this would be a singular Pfaff ideal. If we take the maximal open set that satisfies this condition, the complement would be the singular set of the ideal. Okay, so this is the same that I just said, written in a more explicit way. What we can show is that we can define flat families of differential ideals, okay? And the families over an Artin ring, we can consider families over an Artin ring, in particular families over the ring C of epsilon. So these are the first order deformations of an ideal I, and they are parameterized, they are in bijective, in a natural bijective correspondence with this home, okay, of I into omega modulo I. So this looks formally the same as what happens in the Hilbert scheme. The tangent space to an ideal in the Hilbert scheme is just as home sub O of I into omega modulo I. And here we are taking home over omega, not omega sharp, because in our deformations, we want the integrability condition to be maintained. So it amounts to this home, okay? Okay, we can skip that. And also we can work out the obstruction theory, the obstruction for extensions of ideals, give an element in X1 against sub omega. And in conclusion, we have that the infinitesimal deformations of these ideals has a tangent obstruction theory. So the tangent is this, and the obstruction is this. So once we have this, which is the basically fits into the Schlesinger theory of art in rings. This example is another example of the deformation theory of that kind. Then we can say that if the obstruction space is 0, then the moduli space is smooth at this point. So this leads us to the problem of calculating this hom and this ext. So in our paper with Cesar, which is going to appear shortly, we didn't publish it yet, but it's in preparation, and we are just finishing its preparation. So, we in the first part we developed this standard deformation theory in this case, and what we do afterwards is to develop methods to calculate in examples these homs and these ext ones explicit. So to be able to develop a calculation method for this. One such method is the local global spectral sequence and the associated exact sequence of lower terms, where we have this is the object of interest, and we have here the H0 of the same sheaf, but local. This is global X, and this is local X. So this local X has to do with the kind of singularity. So for example, if the foliation was non-singular, this would be 0. But there are singular foliations, which we call unobstructed singularities, where this sheaf is 0. And then we have that this will be equal to this. Okay. Well, then we have several results to calculate, for example, this local X under some conditions like this is isomorphic to this H1 of this. Okay, calculating over omega sharp is in principle easier than calculating over omega. So because omega sharp doesn't involve the D. In this isomorphism, we still have the D here, but this is a little bit more calculable than this. So this result is useful. Okay, so we have here some explicit situations where we can calculate this omega, this the space of first order deformations. We can calculate as the collections of etas that satisfy this equation, which looks terrible, but it generalizes. It generalizes this equation like this, which is was very much used before in the case Q equal 1. So this is a kind of calculations one has to do to calculate infinitesimal deformations of omega. The first order deformations of omega are all the etas that satisfy this condition here. Okay, so it's very explicit, but still it's not immediate to calculate all the etas that satisfy this condition. It's easy to describe, but not so easy to calculate, actually. Well, let me skip the proof. I have only a few. The proof is very, very simple. So the main example of application of of these results in our paper is the stability of some ideals or stability of FAF ideals. But basically, the idea is that let me say it here. When I have an ideal which is given by Q omega Q1 forms, is the sum, of course, of the ideals given by each of them. And if each of them is integrable and each of these vary in an irreducible component, then our result will imply conditions under which this codimension Q ideal also fills out an irreducible component. One example is, for example, if I take each of them a logarithmic, as I said before, this will give the stability of logarithmic FAF systems of codimension Q. Okay, the theorem of Omega-Calvo is only for Q equal to 1. So one application will be that we can take an ideal like this and say omega-1 varies in one component, omega-2 varies in another component of one forms, and then all this under some hypothesis will describe a new irreducible component of codimension Q. Okay, so this is basically the result. Well, what we have is a little bit more general. So this is this is the main idea of the result for stability of some ideals or FAF ideals. Okay. We also have some condition to imply that an ideal is a smooth point of the Hilbert of the moduli space. And I was planning to, well, I will just say it. I was planning to talk about another problem, which is the stability of pullback ideals. Okay, generalizing the theorem by Servo, Lins-Neto, and Edixhoven that I mentioned before, we can generalize this to ideals. But that's another work in preparation. Okay, so well, let me just keep it, but that's basically the idea. And that's all I wanted to tell you for today. Thank you.
Okay, so let's thank the speaker. Questions? Alessandra? No. No, sorry. Are there any questions? Okay, so we thank the speaker again. Fernando, gracias.
Okay, gracias.